Hello students, in this video we'll be doing some set of problems based on the concept that we have seen in the last two video lecture. So as a first exercise, let us consider a feedback system having two poles, and we have been asked to calculate the magnitude of the closed loop response for different values of phase margin. Now, in order to start up this problem, we need to know what is the definition of this phase margin. So what is the definition? The phase margin is nothing but it is 180 degree plus the phase angle of the loop gain at omega equals to omega gx. So in shorthand notation, I represent that information in terms of phi here. Okay. So what is phi? Phi is nothing but it's the phase angle of the loop gain evaluated at omega equals to omega gx. So what is this omega gx basically? So omega gx is nothing but it is the gain crossover frequency. It is the frequency at which the loop gain magnitude becomes 1. Okay, this is the definition that we have seen in the last lecture, and one could write the expression for the magnitude of the closed loop response as A of j omega, that is equal to the ratio of open loop gain divided by 1 plus the loop gain evaluated at omega. So this is a normal definition of how to evaluate the magnitude of a closed loop expression. But what we wanted is, we want to evaluate the same closed loop magnitude evaluated at omega equals to omega gx. Okay. Now, substituting the value of omega with omega gx, so one would end up with this following expression. Okay. Now, in this expression, let us see how do we evaluate each of the different terms that are involved in this expression. So as a first term, let us see how do we evaluate the open loop magnitude at omega equals to omega gx. So how do we get this particular term? What we know is this particular term, right? So how do we re-express this t of j omega gx? So how do we re-express this? So this also could be written as something like, where t is nothing but the loop gain, which is nothing but it's a product of open loop gain multiplied with the beta factor, okay, and that is equal to 1. So the entire magnitude is equal to 1. Now what we wanted is this particular term, right? So how do we get that? You just transfer this beta towards the right side, and once you do that, one would end up having a result of having open loop gain magnitude at omega equals to omega gx as 1 upon beta. So we have the top term. Now let us see how to express this t of j omega gx. Now what is asked here is not the magnitude. So I cannot plug in this particular value over here. Why? Because it is 1 plus t of j omega, and this whole thing is surrounded by this magnitude. So now I cannot directly go and substitute the magnitude of this 1 in the place of t of j omega gx, right? What we know from our network theory is we can express any system transfer function in terms of Phasor notation. So what is this Phasor notation? Phasor notation is something like, I can express the system response as a product of magnitude multiplied with the exponential term of its phase difference between the input and output, right? So this is my phi, and this represents the phase difference between the input and output, where m denotes the magnitude of the system response. So how do we express the loop gain response in terms of a Phasor notation? So that could be represented as something like this, right? So what we wanted is, we want to express the loop gain quantity at omega equals to omega gx. What we know is the magnitude of the loop gain becomes 1 at omega equals to omega gx. So I can replace this m with a value of 1 multiplied with e to the power j phi. And in this case, the phi denotes this term, that is the phase angle value that we are evaluating at omega equals to omega gx. Say for instance, if our phase margin, okay, so for phase margin that is equal to 60 degree, then one would end up having a value of phi that is equal to minus 120 degree. And how do we get this? It is based on this formula that we have here, correct? So, but I'm not going to substitute this value right now. I'll just hold this phi information as phi itself, and so that I can create a kind of general expression for this closed loop gain. Now let us try to plug in all of these terms onto this expression. So one can write or rewrite the magnitude of the closed loop response as the ratio where the top numerator term could be replaced with 1 upon beta, and I have 1 plus this t of j omega gx, and we can replace that with 1 into e to the power j phi, correct? Now from Euler's theorem, one could express this e to the power j phi as something like cos phi plus j sin phi, right? So rewriting this entire expression as 1 upon beta divided by 1 plus cos phi plus j sin phi, and the whole is surrounded by this mod symbol, right? Now what I have here is a kind of two terms. One is the real part and the second one is an imaginary. So this could be rewritten as something like 1 upon beta divided by the square root of real part squared plus the imaginary part squared, correct? And we know this expansion, right? A plus b the whole square. So one could express this entire term, and when he rewrites, we would end up with something like the square root of 2 plus 2 cos phi, okay? So you can try how to convert this expression onto this expression, okay? Just a simple trigonometry that you have to use it here. So now let us try to evaluate the magnitude of the closed loop transfer function for different phase margins. Okay, so here for a phase margin that is equal to 60 degree, one would end up with having a phase value of the loop gain at omega equals to omega gx as minus 130 degree. Now when you plug in this value of minus 120 degree onto this expression, one would end up with having a value that is equal to 1 upon beta. In a similar way, for a phase margin of 45 degree, one would end up with having phi equal to minus 135 degree. So once this value is plugged in back into this expression, one would end up with having a value that is equal to 1.3 times that of beta. In a similar way, for a phase margin of 30 degree, we'll have a phase value of the loop gain at omega equals to omega gx as minus 150 degree. So when you plug in this phi value, one would end up with having a value of 1.93 divided by beta. So in a similar way, for a phase margin of 5 degree, the phase angle would be minus 175 degree, and one would have a magnitude of the closed loop gain being raised to a larger value of 11.4 divided by beta. One might have a kind of doubt. We know this omega gx is a frequency parameter that is basically related to the loop gain plot, right? But how do we relate that frequency, that is our omega gx, to a different plot? Like in this case, we are trying to relate this omega gx to a closed loop plot. So how do we do that? We know from the definition of the loop gain magnitude plot, the magnitude of the loop gain is nothing but, what we do is, if at all, if I have a kind of graph, this graph represents the open loop gain, say for example a of j omega, okay, And when you have some sort of feedback, okay, so this is my open loop pole, and I have some kind of graph, something like this, or the frequency, and this is my Y scale. Okay, so now for a certain value of beta, we would end up having a kind of closed loop gain which is equal to this value, right? So which would be always lesser in magnitude than compared to our open loop gain magnitude, right? And that's how we draw this line. And what we know is the loop gain could be extracted by taking the difference between the magnitude of the open loop minus the magnitude of the closed loop. So it is this entire region would then map to what is known as loop gain, right? And what is this frequency denotes here, or the frequency at which the closed loop plot intersects with my open loop plot? What is this frequency is called as? This frequency is termed as our omega gx. Now that's fine, but still, how do we relate this omega gx to our closed loop plot? So that is not yet been answered, right? So to answer that, let me try to plot my closed loop transfer function, okay, which is a of j omega. So this would be a kind of line that I'm drawing, which will be straight till the point it reaches this omega equals to omega gx. Now what would happen after this particular frequency? So the closed loop gain magnitude would then follow the open loop magnitude after this particular frequency. Now let us try to take this information and then see how this omega gx could be related to this light shaded green color plot, right? So what I've done here is I've taken this particular part of the graph, okay, and then I have replotted here with another graph, okay. Yeah, so now how do we visualize this omega gx with respect to the closed loop gain magnitude? Now what happens here is the magnitude of this closed loop gain stays almost constant till we reach the value of omega gx. It is after this particular frequency, what has happened is the closed loop magnitude starts rolling off, right? So now what could be this, or how do we visualize this omega gx as? It is nothing but, if at all, if our closed loop gain had a pole at this particular frequency, what would have happened? The same thing, the same kind of phenomena would have happened. So in short, what we can say is this omega gx would act as a kind of the dominant pole for the closed loop transfer function, right? Because if at all, if there is a kind of pole, a pole will have a kind of degradation, right? So at this particular frequency, I might have a single pole or a two pole, doesn't matter. The point here is we are trying to relate this omega gx, which is a frequency term that is related to loop gain, to a pole of our closed loop transfer function. Okay, now let us try to analyze what are these different values that we have for different phase margins. Okay, now let me choose a color. Okay, so in general, what would be the gain of the closed loop when you have frequency that is less than omega equals to omega gx? What we know is we could express this y value to be equal to 20 log of a naught. Now what is this capital A naught? It's nothing but the DC quantity, right? Now, and we also know that this could be approximated to be equal to 20 log of 1 upon beta, right? Yeah. So when we have a phase margin that is equal to 60 degree, what is the magnitude that we have at this omega equals to omega gx? It is the same that we had for frequencies that are smaller than omega equals to omega gx. So what happens is the response would be almost flat till we reach to the frequency that is equal to omega equals to omega gx. Now let us try to go for a phase margin that is equal to 45 degree. So let me choose a red color to represent that. So when we have a phase margin that is equal to 45 degree, what happens is we normally have the same kind of response for frequencies that is lesser than omega equals to omega gx. But the moment we try to reach to the frequency that is equal to omega gx, what happens is there is an increase in the magnitude, and this magnitude is equal to 1.3 of beta, right? So which means that there is a 30% increase in the value of its magnitude when compared to the lower frequencies, correct? So this is how we can visualize this, and after then your magnitude would step down something like this. Now what happens when we step down the phase margin further? So let me take a velvet curve. Okay, so for phase margin that is equal to 30 degree, what happens is we end up having a value of magnitude of our closed loop gain something like this. Okay, so we have the same kind of response for lower frequencies, but the moment we are getting closer to omega equals to omega gx, what happens is the magnitude becomes higher and then it steps down like this. So this value is equal to 1.93 divided by beta. Okay, now in a similar way one can express or one can visualize what would happen when there is a phase margin of 5 degree. So that happens to be a very large magnitude at omega equals to omega gx, and this magnitude is equal to 11.4 divided by beta, correct? Yeah. So let me show you how each of these things are related. I guess when we talked about the frequency response, we talked certainly about something like resonant frequency and resonant peak, right? And when we can have a resonant peak and a resonant frequency in a frequency plot, can you think? So we know that whenever the system poles are complex conjugate, it is something like this, right? There are two poles in the system, and when these two poles are complex conjugate, so what we know is we had a kind of frequency response that had some kind of resonance at a particular frequency, and whenever there is a resonance, there happens to be a kind of peaking, right? And that is what we have over here. So this is the concept that we had already talked earlier during our frequency response. So this is in terms of frequency, right? Now how to visualize a step response when we have an S-plane, okay, when an S-plane having its system poles as complex conjugate. So what we know is when we apply a step input, when the poles are complex conjugate, when the system poles are complex conjugate, the natural response will have a kind of oscillation, and then later on it steps down to its final value, right? And this is the type of response we will have when we have the poles as complex conjugate. Okay, so let me show you a better picture. So in this case, what happens is, like, whenever the phase margin is very small, whenever the phase margin is small, as we have in this case, okay, what happens is we have the magnitude of the closed loop response having some kind of resonant peak happening at some resonant frequency, and this frequency is equal to our omega gx. And if that is the case, what happens is we have the transient response having some kind of resonance or some kind of oscillation that appears across its time response. Okay, and so in this case we can assume that the poles are complex conjugate, whereas when we have a phase margin that is closer to 60 or between 60 and 45, so what happens is we won't find much of peaking that is happening at omega equals to omega gx in our closed loop response. Okay, now in a way that we will have a step response that will be almost smoother, and it finally settles down to its final value. Okay, and this is the type of response we'll have when we have poles, whenever the poles are basically real. Okay, and that is the inference that we can derive from this whole example problem.